Section 2, we're going to get into ionic compounds, that is, ionically bonded substances. And I mentioned already that table salt is just our classic example of this because it is a very common ionic compound. And we've mentioned in the chapter on atoms that chlorine itself is a toxic substance, and sodium by itself is a nastily, very reactive substance. But you put them together and we get a different chemical, and that different chemical has different properties that turns out are absolutely essential for life, although, to be clear, most Americans get way too much salt in their diet. Ionic compounds consist of positively and negatively charged ions, or, as we mentioned previously, cations and anions, and together, those opposite charges attract, forming an ionic bond. And that pattern ends up repeating, as you could see on the salt crystal here, that you don't just have one sodium bond to one chlorine. You have sodiums get surrounded by chlorines, those chlorines get surrounded by sodiums, those sodiums get surrounded by more chlorines, and it gets very big. It's part of why we call it a compound, because it's this complex thing that's made of lots of things, which is also part of why I prefer molecule for covalently bonded things and not compound. But because of that, they tend to have very high melting points, and they tend to be solids at room temperature. There are exceptions to most rules in chemistry, and there are exceptions there, but for the most part, those are good rules of thumb. I mentioned already, sodium, reactive metal, chlorine, toxic gas, put them together, sodium chloride, we have this repeating pattern of ions, and part of why they are different and are safe in this form is because it's no longer sodium with the extra electrons, it's sodium ions. It's no longer chlorine gas, it's now chloride ions, and there is a difference there. We always write them as a chemical formula, so for sodium chloride it's NaCl. However, of course, you know that other substances can have different subscripts. In fact, we saw one in the last section that was CaCl2. And so why a 2 here and only a 1 here? It's an invisible 1, but there's a 1 there. And it has to do with the fact that we are just describing the simplest or lowest whole number ratio of the atoms or ions. We can kind of describe it as either. And it turns out that the total charge of a compound is going to be 0. And so the total negative charge you have has to equal the total positive charge you have to have. I said that backwards, but same thing. Keep in mind we're talking the numbers here and not the signs. So here on sodium we end up with a 1 plus charge, and chloride we have a 1 minus. The numbers are equal. The signs, of course, are not. You can imagine it as if it's an absolute value thing. And so if I put the serifs on there real quick to make it clear that it's different than the absolute value bars, that the absolute value of a positive 1 and the absolute value of a negative 1, those two are equal. But we just need an equal amount of positive and negative charge. And in this case, where we have just a 1 and 1, sodium loses 1 electron to the chlorine. Over here, you can see magnesium wants to lose 2, and so one option is for it to give 1 to one chlorine and 1 to a different chlorine, and then we'll end up with MgCl2, where we have 1, 2 plus, versus 2, 1 minuses. And so then the total there is still 0. Another option would be for magnesium to give both of its electrons to a single element. For example, magnesium has 2, and it can lose both of those, and when it does that, it ends up with the 2 plus charge, and you could lose those to oxygen, which originally has 6. And so then it's going to gain those 2, say, there, and then when it does that, the oxygen ends up with the 2 minus charge, and we would have a formula that is just MgO, because the simplest whole number ratio between a 2 plus and a 2 minus is going to be 1 of each. And it'll make more sense as we get into actually doing formulas here. So here you can see sodium, 2 sodiums losing their electrons to a sulfur, because sulfur needs to be a 2 minus, and so it takes 2 sodiums. And so this time here we end up with an Na2S. And the subscripts can be numbers other than 1s and 2s, but we just saw a metal lose 1 to a non-metal with the sodium and chlorine here. We saw a metal lose 2 electrons to 2 different chlorines, and then here we saw 2 different metals, or 2 of the same metals, 2 different atoms of a metal. 2 sodiums lose their electrons to 1 sulfur. And so the transfer can happen in either direction in terms of which one's giving versus accepting more. And so the way your textbook shows how to do this formula process is we're trying to come up with a formula for barium bonded to chlorine. And so there could be subscripts here. They could be ones, but of course those ones would be invisible. But the question is barium has a 2+. How many of them do we need to add to the 1- times how many chlorines do we need to give us a total charge of 0? And I'm sure you could look at this and kind of figure it out on your own, but if we have a 2+ here, then we're going to need one of them and 2 of these to cancel out with the 1- there. 1 2+ and 2 1- is going to give us 0. It works. There is a much better way to do this, though. And I'm going to show it to you. It's what I call the crisscross rule. And so we have barium. Barium has a 2+ charge. We have chloride, it has a 1- charge. Then what we're going to do is you're going to take the number on the charge, not the sign, just the number, and bring it down here. The number here, and keep in mind that's an invisible 1, and bring it down here. And then you end up with Ba, invisible 1, Cl, 2. And you had the same formula, BaCl2. That is a shortcut to finding it. There's a mathematical reason why it works. I'll give it to you here real quick. Somewhere in algebra, maybe even pre-algebra, you should have learned that A times B is equal to B times A. Multiplicative property, maybe, I don't recall. The term for it doesn't matter. Well, what we're doing is we're treating the charges as A and B. And so we have a 2+ and a 1-. Well, if we multiply this one by 1 then and this one by 2, we end up with a 2+ and a 2-, and then numerically they are equal. Of course, sign-wise they're not, which is why I told you I think of this in terms of absolute values. But we're just taking advantage of that if I multiply chlorine by the charge on barium, and I multiply barium by the charge on chlorine, I'll get the right formula. And the trick almost always works. There is one exception to it, and that is when you end up with the same number on both. So for example, if we had barium bonding to oxygen, barium has a 2+ charge, as we've already seen. Oxygen, if you go check it out on the periodic table, it has a 2- charge. Well, when you do the crisscross thing there, you end up with Ba2O2. We'll fix that 2 there. And now this is correct. This thing is neutral. Two positives cancel out with 2 minuses. However, we do it as the lowest whole number ratio, as the note said, so you have to simplify it. As long as you double check and make sure that it can't simplify, guaranteed the crisscross thing is always going to work to come up with the correct formula. That's how I'm going to handle these. So here, they gave us choices and made this a multiple choice question. I'm going to work it out as if it's not. So here we have an invisible 1, bring that down here on the oxygen. Here we have a 2, bring that down there on the sodium. And we're going to end up with Na2O. Oh, that's that one. Nice that I wrote it right above there. Here, the aluminum, it has a 3+ charge. You'll know that from going and looking it up on the periodic table. Chlorine has the invisible 1 there, 1- charge. So we bring that down there, and we're going to end up with AlCl3, and that one happens to be number 1 here. And then here we bring the 2, bring it down here, and we bring the 3 and take it down here, and we're going to end up with Mg3N2, and that is this one here. And so I'm using the crisscross thing, and again, just to be clear here, it's a shortcut for figuring out how many of each of these you need. Because what we're really saying with, say, this one here is that magnesium has a 2+ and we have 3 of them. Well, 2+ and we have 3 of them, that gives me 6+. And then the nitride ion there, it's got a 3- and we have 2 of them. And so 3- and there's 2 of them, that gives me 6-. 6+ and 6- gives me 0. I have to have a neutral compound. And you've already heard me refer to the names of these somewhat. The next section we're going to get into some more practice on writing formulas as well as how to name these things. But that finishes up section 2.